Starting with a circle, we can draw two lines in the circle that intersect at a point, say, E. Both of these lines cut each other into two parts. What we want to show is that if we make a rectangle out of the two parts of the first line, and a rectangle out of the two parts of the second line, the two rectangles will be equal, or, in other words, the product of the two parts of the first line are equal to the product of the two parts of the second line. There are two cases. The first is when the intersection point is the center of the circle, as so. Then EA is equal to EB, which is equal to ED, which is equal to EC, because they are all radii of the same circle. So clearly, EA times EC is equal to EB times ED. The second case is when the intersection point is not the center of the circle, as so. Pick F to be the center of the circle, then draw FG to be perpendicular to AC, and FH to be perpendicular to BD. Join FB, FC, and FE. Since FG is perpendicular to AC, it has bisected it. AC has therefore been cut into equal parts at G and unequal parts at E. Proposition 2.5 says that AE times EC plus EG squared is equal to GC squared. Adding GF squared to both sides, and noting that since triangle FGC is a right triangle, GC squared plus GF squared is equal to FC squared, we see that AE times EC plus EG squared plus GF squared is equal to FC squared. Since triangle FEG is also a right triangle, EG squared plus GF squared is equal to FE squared. Therefore, AE times EC plus FE squared is equal to FC squared. FC is equal to FB because they are radii of the same circle. So, finally, AE times EC plus FE squared is equal to FB squared. By the same process, we can use FH and BD to show that DE times EB plus FE squared is equal to FB squared. Then, AE times EC plus FE squared is equal to DE times EB plus FE squared. Subtracting FE squared from both sides says that AE times EC is equal to DE times EB.